The next way we're going to determine series convergence is with the integral test. In order for the integral test to be used, we need our function f to be continuous, positive, decreasing, and we need f of k to be equal to a sub k. So for positive integers, our function is equal to our series. And the integral test tells us that either the series and the integral are both going to converge or they both diverge. So if I'm able to evaluate the integral from 1 to infinity and find that I get a number, then I get that this series converges. If I get infinity or that it doesn't exist, my series will diverge. In addition, the value of the integral does not equal the value of the series, and that's an important distinction. Just because I get a number for my integral does not mean that the series adds up or sums to that value. Let's look at a few examples. My first example, the sum from 1 to infinity of k over k squared plus 4. So I'm going to need to integrate from 1 to infinity of k over k squared plus 4. Or 1 over x squared plus 4 dx. In order to evaluate this integral, we're going to do a U-substitution. U is x squared plus 4. So du would be 2x dx, or equivalently, 1/2 du is x dx. When I substitute that in, I'm going to have 1/2 times the integral of 1 over u du. And my bounds, 1 squared plus 4 is 5, and infinity squared plus 4 is still infinity. So this is now 1/2 ln of u between 5 and infinity. So 1/2 ln infinity minus 1/2 ln 5. And keep in mind that this term ln infinity, we're really just taking the limit as x goes to infinity of ln of x, which is infinite. So I get that the integral is infinite, which means my series diverges. Next, I have the series from 1 to infinity of 1 over the square root of 3k plus 2. So I'm going to evaluate from 1 to infinity of 1 over the square root of 3x plus 2 dx. Once again, I'm going to do a U-substitution. I'm going to let u be 3x plus 2. So du is going to be 3 dx, or equivalently 1/3 du will be equal to dx. So this is now 1/3 times the integral of 1 over the square root of u, or u to the minus 1/2. For my bounds, 3 times 1 plus 2 is 5, and 3 times infinity plus 2 is still infinity. Evaluating this, I add 1 to the exponent and divide by that number between 5 and infinity. So now I have 2/3 times the square root of infinity minus 2/3 square root of 5. And once again, this square root of infinity is the limit of the square root of x as x goes towards infinity, which is still infinite. So once again, this series diverges. For my last example, I have the series from 1 to infinity of 1 over k squared plus 9. So I'm going to integrate from 1 to infinity of 1 over x squared plus 9 dx. And when I integrate this, I actually get 1/3 arctan x over 3. If you're unsure how I got that, you can do a trig substitution, but I'm not going to worry about that here. This is now 1/3 arctan infinity over 3 minus 1/3 arctan of 1 over 3. So once again, this infinity is actually a limit, and infinity over 3 is going to tend toward infinity, and arctan of infinity tends toward pi over 2. Minus 1/3 arctan of 1/3. And this term, while I'm not going to outright evaluate it, I can say that it is a constant number. It's not going to be infinite. So I have a finite number minus a finite number, which converges. So this series converges.